Now it's time to look at the most geologically complex world in the solar system, the Earth. As the largest solid world in the solar system, and one with a complex atmosphere and oceans, not to mention life, the Earth shows signs of geologic processes not seen anywhere else. There's no way we can give a complete picture of the ways the four major surface processes play out on the Earth. Even an entire semester course is barely enough to give an overview of our planet's geology. So instead, we're going to focus on just two important processes here: plate tectonics and impacts. Plate tectonics is the grand unifying model that describes the Earth's long-term surface evolution, and it's something we don't see anywhere else in the solar system. If we want to make any sense of the Earth's geology, this is where we have to start. In contrast, impact cratering has been a far less important factor for the Earth's geology. Most craters have been erased or hidden by other processes. However, impacts have had and can still have an effect on life on Earth, including us.
We'll start by looking at plate tectonics. We'll discuss some of the major observations we can make that lead us to the plate tectonic model. We'll look at the forces in the Earth that drive our plate motions. Then we'll focus on the three main types of plate boundaries: divergent, convergent, and transverse. We'll move from there to we'll look at impacts, starting with the tiny bits of rock we call meteors or shooting stars, all the way to the larger impacts that can produce craters, large and small, on Earth. As we'll see, the largest of these could even have affected the evolution of life.
Let's start our look at the Earth's surface by reminding ourselves of what the interior is like. The Earth is divided into a two-layer iron core surrounded by a thick mantle made of rock. The outer core is hot liquid iron. The inner core is even hotter, but the greater pressure squeezes the iron to a solid. The mantle is also mostly solid, but not completely solid. At these tremendous pressures and temperatures, even rock flows very slowly, only a few centimeters per year. This is about the same speed fingernails grow. Because of this slow, fluid motion, the mantle carries heat through convection. Hot mantle rocks flow upward from the interior, while cooler rock sinks back down towards the core. The crust we live on floats on top of this slowly overturning mantle.
Now let's look at the crust. We're going to focus on where we see volcanism and tectonics on the Earth's surface. As we'll see, geological activity doesn't just happen randomly on the Earth. The pattern of how it is distributed gives us important clues that lead to plate tectonics. Here's a map of the Earth's major volcanoes. Notice that most volcanism happens along thin lines, mainly at the edges of continents. There are very few volcanoes in the middles of continents. Note that this map leaves out the ones that are at the bottom of the ocean. The ones you see in the oceans are all on islands. Now compare this with a map of where earthquakes occur. Remember that earthquakes are a sign of tectonic activity on the surface. Once again, most of the action is on narrow bands along the edges of continents, though here we also see many of the quakes that happen in the oceans, also along narrow lines. The key observation here is that these two sets of data overlap. Volcanoes and earthquakes happen in many of the same places, and these places mark out the edges of large, stable regions with much less activity.
This leads us to the concept of crustal plates. The idea is that the Earth's crust is broken up into a series of rigid sections called plates. The central parts of these plates are relatively stable, so they show few signs of volcanic or tectonic activity. However, the places where plates meet are a different story. These plate boundaries are where the geologic action is. This map shows the major plates that make up the crust. The thick black lines mark the plate boundaries, and the red dots are active volcanoes. Notice that there are huge plates like the Pacific and North American plates, along with much smaller ones like the Cocos Plate off of Central America. There are even some smaller ones that aren't labeled here, like the ones offshore from the Cascades Range.
Have a look at this map of the world with the oceans removed. You can still make out the shapes of the continents, although they do look a little distorted. There isn't a smooth transition from continent to ocean bottom. Instead, there's a relatively steep drop-off, just offshore from the continental edges. This reflects a real difference in the composition of continental and oceanic crustal rocks. Oceanic crust, once you get below the sand and silt, is mostly made of basaltic rocks. These are fairly dense as crustal rocks go. On the other hand, the continents are mostly made of granitic rocks. Granites are much less dense, and the continents also form a much thicker layer. While the ocean crust is typically only 10 kilometers thick, the continents can be 50 or more kilometers thick. The combination of lower density and thicker layers means that the continents stick up several kilometers higher than the oceans. Those drop-offs at the edges of continents mark the boundaries between the two types of rocks. So notice that some plates are virtually all ocean, like the Pacific Plate, while others have a mixture of continent and ocean. Look at how the North American Plate extends out to the middle of the Atlantic Ocean. The drop-off from continental to oceanic rock happens within this plate, so one plate can have two kinds of rock.
Plate tectonics is the motion of these crustal plates. We should think of the crust as floating on top of the denser mantle. Remember that the mantle is undergoing a slow convective motion. Hot mantle rocks rise and cooler rocks sink, creating a constant overturning motion. The crustal plates are dragged along with this flowing mantle, with new plates forming in some areas and old ones dragged back into the mantle in others. So the power source behind plate tectonics is the Earth's internal heat, causing the mantle to flow. There are three major types of plate boundaries. The first is a divergent boundary. This is where two plates are pulling apart. The next is a convergent boundary, where two plates are squeezing together. The last is a transverse boundary, where two plates slide past each other. Let's look at each of these in detail. At a divergent boundary, two plates are pulling apart from each other. This happens at the places where hot mantle rocks are coming up from deep inside the Earth. So the mantle rocks squeeze up between the plates and create new crust on the edge of each plate. When this mantle solidifies, it produces basaltic rock, so the new crust that forms is oceanic crust. The most common kind of divergent boundary on the Earth is a mid-ocean ridge. These are long mountain ranges running through most of the world's oceans. They form from the upwelling mantle, and they show many volcanic features, like this black smoker underwater volcano. There are also many earthquakes along these boundaries. This map shows part of the Atlantic Ocean, with the mid-Atlantic ridge running down the middle of it. Notice that it bends to follow the shapes of the coastlines on either side of it. Mid-ocean ridges and their surroundings were some of the first features that truly convinced geologists that plate tectonics was a good description of the Earth's geology. This happened because geologists noticed that the age of the ocean crust follows a very special pattern. Along the ridge, the crust is always very young, getting progressively older as you move away from it. In this global map of the oceans, you can see that it's a very symmetric pattern on either side of the ridge. Clearly, the ocean crust has grown from the locations of the ridges, spreading outward in either direction. Notice something else about this map of ocean crustal ages. The oldest part of the ocean crust, shown in dark blue, is less than 200 million years old. In comparison with the over 4 billion year age for the Earth as a whole, this is a very short time. On many parts of the continents, it's not unusual to find rocks that are hundreds of millions to a couple of billion years old. So the ocean crust is clearly disappearing just as fast as it's being formed. We'll come back to this observation shortly.
Sometimes the mantle upwelling happens under a continent instead of in the middle of the ocean. When this happens, the continental crust begins to thin and eventually split apart. This creates a feature called a rift valley on the continent. These are characterized by active volcanoes, long, narrow valleys, and lots of earthquakes. The best example of this on Earth at the moment is Eastern Africa, where a set of rift valleys extend along much of the eastern half of the continent, threatening to split East Africa away. This has already happened further north, where the Red Sea divided the Arabian Peninsula from northeastern Africa.
Using a variety of clues, geologists have plotted out the motions of the Earth's crust over the last several 100 million years. And this shows how rift valleys have evolved into oceans over time. 255 million years ago, the Earth's major continents were all joined together into a single supercontinent we call Pangea. Some areas that are now joined together were widely separated, and some areas that are now land were covered with shallow seas, like western North America in the upper part of this map. Pangea wasn't the first supercontinent, but it's the one we can piece together most easily because it was the most recent one. By 195 million years ago, early in the era of the dinosaurs, much of Asia had split off from the rest to form an early version of the Indian Ocean. Notice that India was wedged in next to Africa, and a new mountain range was developing along the west coast of North America. Also, a rift zone is developing on the east side of North America, splitting it off from Africa. By 150 million years ago, Europe and Africa have split away from North America, though Africa is still solidly linked to South America. Another major rift has developed between East Africa and India. Just over 90 million years ago, a rift between Africa and South America has widened enough to justify the name South Atlantic Ocean. India, Antarctica, and Australia have also split off from Africa, and a new shallow sea has developed just east of the Rocky Mountains. The great dinosaur fossil beds in places like Montana and Wyoming are developing along the edges of this sea. By 50 million years ago, after the dinosaurs had died out, the shapes of continents are getting mostly recognizable. The Atlantic is getting wider, though still not as wide as we see today, and Australia has diverged from Antarctica, and both India and Australia are moving rapidly north towards Asia. Notice that Arabia is still attached to Africa at this time, although much of it is also underwater. Also, North America is approaching an old mid-ocean ridge in the Pacific Ocean. Now we come to our present world. The Atlantic is still getting wider, Africa is moving north and has almost closed in the Mediterranean Sea, and India has crashed into the southern edge of Asia. North America has run over the East Pacific Ridge. Where it crosses this ridge, a new kind of split has developed along the west coast. We'll talk about this one later. We can project this motion another 50 million years into the future. At this point, the Atlantic is now getting almost as wide as the Pacific. Africa has closed off the Mediterranean Sea completely, and Australia has moved up into Southeast Asia. Eventually, in a couple of 100 million years, the continents will all join together again into another great supercontinent, until it too is split by rift zones into a new set of continents.